In this video, we'll talk about similar polygons, what it means to be, or for two polygons to be similar, and what you can do once you know two polygons are similar. So let's talk overarching definition of what it means for two polygons to be similar in a geometric sense. So I would say two polygons are similar if and only if the angles are congruent. And I suppose I should mention angles pairwise are congruent. And the side lengths are proportional. So in essence, if we're thinking about a similar figure, it can be basically a zoomed in version of the figure, so basically an enlargement where everything is kept to the same specification, or it can be something that's shrunk down. And kind of a couple of popular examples here. One would be like a model car or a model plane. Everything is kept in the same ratio, but it's just been shrunk down. Likewise, if you think about like a blueprint or a floor plan, same kind of idea. You reduce the size, that way you can look at the entire thing all at once. So this is very useful in a lot of ways, and it's worth just kind of talking about this from purely the mathematical perspective of polygons. And we have to be very careful about this and piece. This and, the side lengths have to be proportional. It usually gets tossed to the wayside, and there's a couple reasons for that being. But one reason we mention it is, okay, if I have a square, well, all these are 90 degrees, but I would not say it's similar to this rectangle. This square is not in any way, shape, or form a blown up or shrunk down version of this rectangle, or vice versa. So just keep that in mind. The and is a very important part of this definition when we're talking about polygons. So let's say, hypothetically, we were given the knowledge that figure A, B, C, D is similar to, and you write this with this kind of single squiggly line, it means similar. And again, we have to be careful with our order here, just like we're talking about congruence. So A looks like it corresponds with E, B with F, C with G, and D with H. So if I'm allowed to say those are similar, there's a lot of things I can say here. I can say angle A is the same as angle E. Angle B is the same as angle F. I can say angle C is the same as angle G. And I can also say that angle H is the same as angle D. I can basically get all of those angles for free if these two figures are similar. Now, hypothetically, if I was given a side length on, say, AB, let's say AB was 5 and EF was 20. This would mean that the rest of these sides are scaled up by a factor of 4. So I could say AC, so 4 times AC, is equal to EG, for example. Or I could say a fourth of AG is AC. There's a lot of ways we can use this to our advantage. So basically we can set up proportions if we like to solve for missing lengths. That's just kind of one thing that's useful. We can also test this if we want to. So for two figures to be similar, all of these things that I've drawn here have to be true. If we find one case where it's not true, so say hypothetically, I didn't know they were similar, I knew all this information that I have here, and then I have 7 and 32 here, well, 7 times 4 is not 32. So I would be able to say these two are not similar in this case. So it's worth mentioning if you have an angle that's not the same, or if you have one side length where that proportion doesn't always hold true, where the ratio between the sides isn't always the same, then you can deduce that it's not similar. So just kind of some overarching themes here on similarity. We will talk more about specifically triangles in similarity because you get a few more things there. But largely we're talking about solving for sides or determining if something is similar or not based on information that we're given.